My name's Laura Taalman, and I'm a math professor at Madison University, and today I'm going to talk to you about using technology to explore mathematics, which 15 years ago I would have not believed it if you told me I was ever going to say that sentence out loud. So when I finished my PhD, I was a very pure mathematician. To me, using computers or any kind of technology with my mathematics would just be unheard of. I just would not have done it. And like many things in my life, I was just totally wrong about that. And so I want to talk to you about ways that I'm using technology now to help, in particular, undergraduates who are just learning to do mathematical research. So the example I want to use to start out with is that of knot theory. And you see behind me some knots drawn on the board. A knot is just a string that's been knotted up in some way, and then the ends have been attached together again. And the kind of thing we want to know about with knots is when are two knots the same and when are two knots different. So if I take a piece of string and I tie it up in one way, and I take another piece of string, I tie it up in another way, how can I tell if those are the same knot or if those are different knots? So it's not enough just for me to give up while trying to change this knot into this knot and then say, well, I can't do it. I have to actually have a reason why this knot can't be bent and twisted without breaking into the other knot. And so knot theory is a lot about that. And so, for example, you might associate a number to each knot. So to each knot, say you take the knot 6-2, which you see on the board, the bold one there, and another knot, say 6-3, the next one in the knot table, and you do some mysterious process that allows you to assign a number to each of those knots. That number that I want to talk about is called the determinant. Now, I don't want to get into the details because I just sort of want to tell some stories in this video about how I'm using some technology. But just rest assured, there's a way that we could label the strands and crossings and create a matrix and take the determinant of minors, and then that would be this thing that we call the determinant. Okay? So 6-3, that knot gets a determinant. 6-2, that knot gets a determinant. It turns out that one of those determinants is 11, and the other one of those determinants is 13. And so the determinant is what's called a knot invariant. Since I got different determinants, I know for a fact that they were different knots. If I got 11 and 11, I would not have known that they were necessarily different knots. But if you get two different things, you know you have two different knots. So I've been working with some students studying something called spiral knots, which is a very regular kind of knot, and using computers and Mathematica to compute huge sets of data about these spiral knots and then be able to go find patterns and look it up in the online encyclopedia of integer sequences and prove those patterns. And that kind of exploratory avenue is what's new for me with technology and using it to study pure mathematical topics. Another example is singular knots. You may have noticed that one of the knots behind me has a big dot on it. It has a singularity where the two strands have kind of been fused together. Singular knots are used a lot. There's lots of papers about singular knots and their connections to Vassiliev invariants and all kinds of fancy things. But my students and I realized that there was no table of singular knots. There was no list of them. Like we tried to find out how many 5 crossing 1 singular knots are there, and there wasn't a list of that. So we thought instead of proving a lot of theorems, we would try to make that table, which is like a crazy, ridiculous idea that we knew we would ultimately fail at because it's difficult to know if you missed a knot or whatever. But anyway, we used computers extensively figuring that out because at each of those singularities, we can resolve that singularity 4 different ways. And so then the invariant for the singular knots is actually a set of regular knots. And to tell if 2 singular knots are the same, you check and see if the 2 sets of associated knots are the same. So now you have all these invariants to compute, and then once again we can use computers to try to get like huge data sets, find out what's going on, look at all possible combinations, and get a table of singular knots. So we made the first table of singular knots up to, I think we went through like 8 crossings of that table of singular knots. But all of these knots are flat. I mean, I wrote them on the board, right? And so they're 2-dimensional sort of representations of knots with crossings and strands. And we like that because then we can label the crossings and label the strands and do some nice combinatorics on the knots. But they're really like 3-dimensional animals. They sit in 3-dimensional space. And Jason Cantarella and some students at the University of Georgia used gradient descent to find these sort of optimal conformations of knots, these minimal conformations. So they're minimal in terms of how much rope is needed or how much energy is used or whatever your metric is. They're somehow like ideal configurations. And these configurations came with a set of data describing them in space, and we realized that we could actually print them. So we could take this data, put it into Mathematica, and then actually make one of these knots. So this would be very difficult for me to draw on the board and for you to be able to see all the different ways this knot looks depending on how you look at it, and maybe try to think about developing a notation for knots in 3-space instead of knots on the board. These are crazy, ridiculous questions, but that's, you know, it's new. And so there's a good avenue for students to just explore and do crazy things. What can you do with this? So let me give you an example. Here's 2 knots. The yellow knot is 818. It's a very beautiful symmetric knot. The red knot is a horrible, angry looking, just wrong knot. It's not very nice. This is 819. This is 818. That just means that this is the 18th knot with 8 crossings in the table, and this is the 19th knot in the list of the knots with 8 crossings, okay? And this red knot has a very special property. Its property is this: no matter how I draw it on the board, I will never ever be able to draw it so that the strands go over, under, over, under, over, under, like they do in all the pictures that are on the board here. You can't do it. So you can draw it on the board, but it wouldn't be alternating. This is the first non-alternating knot. This is the knot right before it in the table. It is alternating. So my question is, how could we tell that just by looking at this, right? Not by examining projections or other things, but with this. I don't know the answer to that because I just printed these recently, but that's the kind of crazy question that I hope we can investigate now that we can actually hold these in our hands. So here's another example, the Bromian rings. That's three rings, no 2 of which are linked, but all together they're linked, okay? Now the Bromian rings are a very famous object, and when I had a 3D printing class last spring, I told the students, go and 3D print something mathematical, I don't care what it is. And one of the students in my class came back the next week. She had decided that she wanted to print the Bromian rings, understandably, because they're beautiful. So she did this. She printed them. They were beautiful. They were all separate, and it looked really great. But she said, I have to tell you something. I worked for hours to make these out of circles. I worked with the modeling program for so long, I could not get 3 circles to be arranged so that no 2 were linked, but that altogether it was linked. I just couldn't do it. And so finally I gave up and I made them ovals. So I know they look like circles, but they're actually just a little bit like ovals. And so I just want to let you know that I had to cheat. And I'm sorry, I'm not even sure it can be done for circles. That's what she said. Now it turns out, it's a well-known fact in knot theory, that Bromian rings are impossible with circles. You cannot make them with circles. That's like one of the things about Bromian rings that's cool. But she didn't know that. So she got to discover that herself by being frustrated, actually come to that conclusion herself, which I thought was really amazing. And even better, I knew this fact, right? I knew this fact about the Bromian rings, but it wasn't until she handed me the model that I was like, oh, of course you can't make this with circles. That would never work. Like immediately you can see. So things that are difficult to see become obvious. And students can discover things that for us we may not have learned about till a long way on in our career. So here's one final example. I had a student, another student, he wanted to write a computer program that would take any 3-dimensional model that you have in the computer and it would rotate it so that 3 points of it were sitting flat, at least. So, you know, like for example, if you were printing this, you don't want to print it on its corner because it would not be very stable, right? You needed to be having some contact with the platform, and he wanted to make it so that every knot we printed, you know, actually sat on 3 places. Now, I didn't know how to do that, but I started looking into it and discovered that there's an example of a knot that can't sit on the table like that at all. Okay, so here's this example. This knot has no tritangent planes. No matter how I put it down, it will never ever hit the table in more than 2 places. In fact, even if the table could somehow like go through the middle, there's no tritangent planes in there either. It just rolls around like kind of an infinite rocking chair. And when I bring this to mathematicians and I say, you know, oh, did you know there's an object that has no tritangent planes? They say, well, that is impossible. And then I have this thing. And they're like, oh, it's totally possible. And it's obvious how it works. So it's very exciting to actually hold these things. The paper that we got these equations from, these parametric equations to make this knot, it didn't even have a picture, like not even a 2-dimensional picture, okay? And then now we can actually hold it, which I think is really exciting. So what I hope is that these examples have convinced some of you to buy 3D printers for your math departments and just set your students loose to print beautiful things on the printer. You don't need a specific reason to buy it. it will just sort of happen that your students will think of lovely things to print and you'll be surprised. So if you do that, please let me know because I would love to know what you make. Thanks.